Today, I will try to help you understand the Schrodinger's equation as intuitively as I can. By now, you have seen this formula. You also know that it signifies the total energy of the wave function equals to the sum of its kinetic energy plus the potential energy of the wave function. But what I would like to discuss here is significance of I, or the imaginary part. The imaginary part is what we struggle to visualize. And on a channel named Visualizing Math and Physics, if you haven't got at least some visual clue of a math or physics formula, then what is the purpose of this channel? So let's take this formula, bit by bit. One part at a time, shall we? So, let's take this term first. We will consider the I in the formula later. But first let's know the significance of this term. The rate of change of wave function with respect to time. That is what this particular term means. The rate of change of wave function with respect to time. The partial derivative means that you are measuring the rate of change of wave function exclusively with respect to time and time only. So the changes in the wave function with the passage of time is all that you are considering. That is what the partial derivative signifies. Is this much clearer? So imagine that you take a photo of the wave function. Now imagine after some time you take another picture of the wave function. Now imagine you are taking a series of pictures of the wave function. At what rate does one picture change with respect to another as time passes? That is what this term means. Now, what if I is also conjoined with this? Now, I stands for imaginary part. Now, real part and imaginary part of complex numbers comes into math whenever one whole influence gets divided into two daughter influences. I have explained this in detail in Visualizing Math Part 1 and Part 2. We call one daughter influence as the real part, and the other daughter influence as the imaginary part. In this particular case, the imaginary part is the side view of the wave function. So, I into partial derivative of wave function with respect to time means you are considering only the side view of the rate of change of wave function. And simultaneously you are ignoring the top view of the wave function. The top view of the wave function is the real part. This means that you are considering only the side view of how fast the wave function is moving with respect to time. Now, because we are dealing with a wave function which looks exactly the same whether you look at it from the front or from the side, it looks the same. Unlike, say, a chair, which looks different if you look at it from the side as opposed to if you look at it from the front. In other words, the side view of a chair is different from its front view. For a wave function, the side view is the same as the front view. And the front view is what you are watching of the wave function on your screen. So basically you can say that the total energy of the wave function is equal to the front view or side view of the rate. But first, what if there was an e-book that explained major concepts of math using simple and everyday examples and analogies? What if sine theta is a measure of how much perpendicular two forces or objects or influences are with respect to each other? So a roof which is perpendicular to the flow of snow, won't it collect more snow than a roof that is less perpendicular? Now, coming to cos theta. Cos is a measure of how much parallel two forces or objects or influences are with respect to each other. Say two forces push a drum. Won't the maximum effect be when these forces are acting parallel to each other? Complex numbers. They come into math whenever one parent force or influence gets divided into two daughter influences. You can call one daughter influence as the real part and the other daughter force as the imaginary part. What if the base of logarithms is the rate at which change takes place? What if log of a number gives you the cause for every effect? In calculus, dx means keep adding along the x-axis. D means keep adding along the y-axis. Doesn't means keep adding along the z-axis. D theta means keep adding along a vertically curved plane. Deep psi means keep adding along a horizontally curved plane. DH means keep adding along increasing height. Doctor means keep adding along increasing radius. Also, what if integration and differentiation are reverse processes of each other? Add disks one above another along a height, you get a cylindrical structure. Thoughts integration. Remove disks along height, you get circles. Divergence is the rate of change of a quantity, for example heat, along the x, y and z axis simultaneously. What if curl is a measure of how much a field can make you spin? What if I, j and k in the formula indicate different planes of rotation? What if the diagonal of a matrix is the axis of rotation of a matrix? What if all these intuitive examples and understanding is explained in one single ebook? More such concepts explained intuitively. Link is given below in description. Of change of the wave function with respect to time. Likewise, the real part of the wave function will be the top view of the wave function. So the more you see the wave function changing with the passage of time, that means the more total energy the wave function has. This term that you are seeing now is the LHS of the Schrodinger's equation. Now let's go to the terms of the RHS of this equation. So rate of change of wave function with respect to x-axis is denoted as the single partial derivative with respect to x. And rate of change of wave function is what is denoted as the double partial derivative with respect to x. If there is a rate of change, that means we are dealing with a curved graph. Also, it can be shown as a double derivative. So this term is the rate of change as you move along the x-axis. This means that the slope of the wave function graph will be curved. This is because the rate of change with respect to x-axis has another intrinsic rate of change within itself. Very similar to how velocity is rate of change of distance and acceleration is rate of change of velocity.
The real part of a building, for example, is the top view of the building. Now, if your goal is to find the number of floors in that building, obviously this view doesn't make a lot of sense, does it? For that, you need the front view of the building. This front view, in this case, is the imaginary part of the building. The similar is the case with real and imaginary parts of the rate of change of wave function. In the case of the Schrodinger's equation, we ignore the real part, or the top view of the wave function's rate of change with respect to time. And we focus solely on the imaginary part, or the front view of the wave function's rate of change with respect to time. Because this view is what gives us an idea of how the probability zones change with respect to time.
How much total energy the wave function has depends on how much rapidly the wave function moves with respect to time. And we are concerned only of the imaginary part of this rate of change. That means for a circuit, the real part would mean resistance and imaginary part would mean capacitance. Resistance would be burning the electrons, capacitance would be delaying the electrons. Whenever one influence gets divided into two daughter components, that is where we have real part and imaginary part coming. But this can, so imagine a radar which is showing just how much upwards the aeroplane is moving. We are not concerned with the other daughter component right now. That is how much forward the aeroplane is moving. That is what the imaginary part is. So I